All right, guys, so a couple more videos here today, and then I hope to be back on Monday so that I can finish out the rest of this section and the next with you in class. But let's get started on the 8.2 notes here. So what we're going to see in this section is really just a lot more practice with representing our function. So we've seen kind of the variations of our function, right, where we've seen the phase constant come into play. We'll get a lot more practice with that, and then we'll see a little bit more on how we can apply this for both spring situations and pendulum situations, right? So we're going to look a lot more at like simple harmonic motion in this chapter. But if you look at that first diagram, I know it's pretty busy, but I would expect you, if needed to be able to make a kind of a motion diagram of a block if it were oscillating back and forth. So if we break this down and kind of think about it, let's make sure we're comfortable with what's going on. So when we're at either amplitude, right, we know at that moment in time, the velocity when it's at either amplitude should be at least momentarily zero, right? We know that either end, when the block reaches that end, it's going to momentarily stop before turning around and going the opposite direction. Whereas if I look at the velocity vectors, which are again the green vectors, it will be at a maximum velocity when it's passing through that equilibrium position, right? And so that's when the magnitude there should be the highest. Notice at that point, the acceleration would be zero. And that's because if we're talking about a spring, right, if it's k times x, when it's in equilibrium, that's when the x would be zero, right? The net force would be zero at that location. And therefore, the acceleration would be zero, too. If they ask us where's the acceleration the highest, the acceleration is going to be the highest at either end again, right? So if I look at either the positive amplitude or the negative amplitude, that's where the acceleration is going to be at a maximum value, is at those 2 points. And so that's what this graph is trying to show us, obviously, as this is oscillating back and forth. They're actually, I guess, showing us there on either side right there. But like I said, be comfortable interpreting these graphs. Not terribly difficult if you're doing just a motion diagram, but be comfortable interpreting that and then be comfortable making that as well. And then let's talk again briefly about these functions, which we've already seen. So this first function is just representing kind of our standard, right? X equals a times cosine of omega t. Now, if I'm looking at this graph, I know that there's not a phase shift because it is starting at the positive amplitude. So I don't have to worry about any type of phase shift for this particular graph. We, of course, could do that in general, but we won't worry about it here. We also, remember, won't always use omega. A lot of times we might do 2 pi times the frequency or 2 pi over the period. And we'll see a little bit more with that as well. But we know that we've already seen this a couple times as it is, right, and started with this a few times. Remember that if I do the derivative of this, I end up getting, it'd be negative sine, so it'd be negative a sine, and then because we do the chain rule, when we do the derivative of the inside function, we would get the derivative of wt, which is just w, right? So the derivative of this, which gives us just w. And so then that would pull out negative aw out front and then sine of omega t. And the reason that that's important is because that first chunk, like we saw a little bit in the past, but that first chunk is what gives us the maximum velocity. So if they're asking us to find the magnitude of the maximum velocity, we could simply do that by doing negative a times w. And then if I take this a step further to find the acceleration, which is what they've done here for this graph, the acceleration function would be the second derivative, which would simply be a times w squared, and then back to cosine of omega t. We just do that derivative one more time. Sine becomes cosine. It stays negative because it was already negative. And then the derivative of the inside adds another omega out front. And again, the reason that that's important for us is because that first part right there, that coefficient out front, represents the maximum acceleration, right? Now, it is important conceptually that we know where the maximum velocity and the maximum acceleration would occur at. And so again, relating that back to our position versus time function, the maximum accelerations would occur anytime we're at the amplitude, right? And those accelerations would be going in the opposite direction. So when I'm at the positive amplitude, my acceleration would be negative. When I'm at the negative amplitude, my acceleration would be positive, and vice versa, right? Whereas the maximum velocity, I'll go ahead and label those points here in green, right? The maximum velocity is going to be happening anytime we pass through equilibrium. So if we can just find those values, we know exactly where and when they'll be happening on this graph. So if I look at this picture, kind of gives me the initial setup right there for me. So in this first case, the velocity would be going in the negative direction because I'm going from positive to negative. But then in the next case, obviously coming back the positive direction. So we can do a lot to break that down. This second graph is obviously just, again, trying to show us what the acceleration is doing. It's still following the same cosine type curve, but it's showing us that at the amplitudes, the acceleration is actually the opposite magnitude, right? So instead of being at the positive amplitude, that's when the acceleration is a maximum negative value for that graph. But anyway, hopefully this kind of makes sense as we look through that. Before we get on into the first example, I actually do want to show you guys a derivation. It involves some of the calculus that we can take advantage of now. And so basically what I want to show you guys is we know the period for a spring. If you recall, the period for a spring is 2 pi square root of m over k. We've seen that before, right? And we talked a little bit about last year about how you could derive that algebraically by taking advantage of circular motion. But I actually want to show you using calculus how we can derive that. And that's by starting with the net force equal to the only force that's causing it. So if it's a spring and it's oscillating back and forth, the only force that's acting on this system would be that spring force, which is negative k times x, right? And I am going to include the negative because the negative is indicating that it's the opposite of the direction of whichever way it's been displaced. So if this is in equilibrium, then at this point here, right, if this is the positive displacement or the positive amplitude, then the force would be in the negative direction. So I am going to go ahead and include that negative value there. So my net force equals negative k times x. We know that. This side, I'm going to go ahead and break it up into mass times acceleration equals negative k times x. And then the trick on this derivation is I'm actually going to get both of these terms on the same side. So I'm going to add the kx over. Now it's equal to 0. And then I'm also going to go ahead and divide both terms by m. You don't have to do this right away, but I'm going to go ahead and do that to simplify this down a little bit. So I get k over m times x. I'm going to go ahead and write it out that way. Now, the reason that I do this is we actually have two different functions represented here, right? We have the acceleration, which we know changes over time. We also have the position, which we know changes over time. Now, k and m, fortunately, are both constants, but acceleration and position change with time. The good news, though, is we know what functions represent both the velocity, both the position and the acceleration with respect to time. Our position is represented by this. If we do the second derivative, right? So x prime would be, we know, negative sine, all that fun stuff. If I do the second derivative, that would be my acceleration, which is negative a omega squared times, cosine of omega t. And so we already know this. Hopefully we're comfortable proving that, right? I do expect you guys to be comfortable deriving that if need be. But what I'm actually going to do then is I'm going to take both of these and substitute those in for my acceleration and for my position. So I'm going to plug in negative a omega squared cosine of omega t, and then plus the km is just going to hang out front for me, and then times a cosine of omega t. And then I'm going to, since it's equal to 0, I'm going to go ahead and factor out what I can. So they both have an a and a cosine of omega t in common. So I'm going to go ahead and pull out the a cosine omega t. And then that would leave me with negative w squared plus k over m. And then this whole thing, of course, equal to 0. Well, because of this, right, if I were trying to solve this equation, I know that if I were trying to find like the zeros of this equation, I could either set this function equal to 0, which we could figure out, right? That'd be easy enough to solve for what values of t give us 0, right? But the other thing we could do is, and this is the part we're going to look at, is we can now take that inner portion there. We're going to take this part of the piece, right? And we are going to set that equal to 0. So I'm going to set that equal to 0. I actually don't like that red as much, so I'm going to switch to white here. But anyway, so if I then take this and solve for omega, I can add the omega over. I get omega squared equals k over m. And when I do that, I then get omega equals the square root of k over m. So what this shows me is omega relates then to the spring constant, and the mass. Now that by itself may not seem particularly helpful, but if we recall, omega is really just equal to 2 pi times the frequency, right? Remember, frequency is measured in cycles per second, and omega is measured in radians per second. So really all I'm doing is taking the number of cycles per second and converting it to radians per second. So that's all I've done so far with that, right? Well, if I do that, this is helpful because this actually shows me the relationship then between my period function. So if I take 2 pi times the frequency equal to the square root of k over m, so all I did was I plugged in my 2 pi f for omega, and then if I solve for f, that's where I get 1 over 2 pi times the square root of k over m. This hopefully looks somewhat familiar from what we did a lot of last year, right? And sure enough, because the period is simply the reciprocal, right, of the frequency, if I were to find the period, it would just be 2 pi. So 2 pi over 1, I'm flipping that over, and then the square root of m over k. And that proves, I'm going to put this little box here because that's what we do sometimes, but that proves that the period is 2 pi square root of m over k, which is an equation we've worked with for years, but it's kind of nice to be able to see. Oops, sorry about that. Trying to find my toolbar up here for my PowerPoint. But that shows me then what I was trying to see, right? In terms of this shows me the relationship of where that period comes from. All right, sorry, give me just a second, guys. I'm going to try to figure out what's going on here. All right, sorry about that delay. I know that was a really exciting 30 seconds right there. But anyway, so this is a proof of where our period function comes from for a spring system. It shows us where that period comes from. I do want you to be familiar with this. Not necessarily that it will be like straight up asked on a test, but it could come up on maybe an AP exam or something where they ask us to prove this. It's definitely a little complicated, but I did want to take the time in this video to show you where it comes from. Like I said, kind of an interesting derivation for it. I'm going to go ahead and stop the first video here because I know I definitely won't have time to get through the first example if I continue. So I'll stop this first video, and then you have another video to see the first example or two.